Definitely.
Okay, 1 minute to go. Yeah, hello, welcome everybody to our next lecture within our seasonal school on network federated learning. We have the great pleasure to have an expert from industry, Dr. Tavakoli from Nokia, telling us about compact and efficient neural networks, steps towards communication efficient federated learning. Hamed is a principal scientist at Nokia Technologies here in Finland. He has been leading the neural network compression and federated learning team over the past few years. Prior to joining Nokia, Hamed was with Aalto University, where he worked, researched machine learning with the focus on computer vision and its intersection with natural language processing. So very happy to have you, Hamed. Please take it away.
Thank you so much, Alex, for the introduction. And hello, everybody. So in this, I would call it a short talk. I'm going to touch different topics, and then we will basically just get a very brief introductory we will have a very introductory talk about the efficient neural networks, and then the communication efficient federated learning. And this is coming more from a practical point of view in the industry. And I'm leaving actually quite deal of material that could be studied basically personally based on interest, and just will give some cues, what could be the keywords and what could be the directions to look for if someone wants to research in this area. So I keep things very, very simple, not going into many details, and we just try to chat about the ideas and concepts. And please feel free to stop me while you're moving forward. And if there's some questions, we could try to address it immediately. Let me start with basically a little bit of a teaser. Nowadays when we talk about the AI and machine learning, everybody has something to say about the deep neural networks. Actually, deep neural networks has at a point in time people were associating it, everything AI is deep neural networks, and it started like gaining quite a good market in the world. So for instance, with the survey that they did in the industry, and then the predictions, they are expecting that we are going to have a market of $6 billion by 2027, and that would be only on the products that are relevant to delivering deep NNs, and not the things like the TensorFlow, PyTorch, or the frameworks that are facilitating deep neural network based solutions. And if you take into account the verticals that could be built on top of that, for instance, the 5G services that one could build on top of this, or the future 6G, the metaverse, AR, VR, then this market is actually quite huge. And that could trigger many people to research in this area. So Given this, let's have a look at how this went on over the years. So, when we go through the literature, in up to 2017, most of the neural networks that we were facing, they were sort of, handcrafted. So the first one that won the ImageNet competition, the AlexNet, back in 2013-14 timeframe, it was quite a revolutionary thing because it beat basically the performance of the ImageNet classification by great margin. Then people in computer vision started basically shifting to the deep networks, for instance, and then it came the VGG and ResNet and the Inception and so on. So many of these networks, they were designed with some idea or expertise of a person who was trying to take some knowledge of computer vision into the deep nets. For instance, in VGG, you're going to have the kernels 3 by 3 because it has, you have the insight that it has good properties for processing, the visual tasks. But then what happened was that, we started having, very big neural networks. So for instance, in terms of the number of the operations that are needed to calculate VGG, you see for VGG 19 at almost 40 giga operations, and then the memory that they require to be in the memory requirement is quite huge. So people started, then trying to compactize them and make these networks small. So this compactization has, some benefits. If they could do the same job with the smaller networks that needs less memory, and then it needs less computation power, that allows us to put this, for instance, on a mobile device. So, up to 2017 timeframe, we see the dominance of these handcrafted, deep nets. So by handcrafted, it means those that have the architecture handcrafted. Then around the 2016, 15 to 2017 timeframe, we see a paradigm shift. That's, when, why don't we automate the neural network construction, or why don't we make these things compact? So that's when we are seeing that people are revisiting some old ideas, such as the neural network search or model architecture search, which is basically reintroduced as AutoML and NAS, neural architecture search. And it was started that we see that people are putting different constraints, and then they just, search for the best architecture. And we see the architectures like the MassNet or the efficient net that are emerging. But of course, the AutoML could be very expensive. So we see that many of the models that are coming from the AutoML part, they're belonging to big companies. Of course, they are available to the public, and we could utilize it. But as the competition is fierce, there are people who said, why don't we revisit the other way of compactization? Why don't we prune, sparsify, or we don't use the decomposition-based methods? So it's another way of compactization. I have my model designed by an expert, and then what I do is I use basically some criteria for getting rid of those connections, neurons, and elements in the neural network that doesn't really help the job. So there are people who took this path. Some of the people decided that we could basically find a better representation instead of for having these filters in the convolutions. We could decompose the filter matrix into the smaller matrices, which actually needs less a space to store, and then, with some tricks, it could be faster to compute. So people started to visiting these old ideas. So these ideas actually, they are back to the 80s and 90s of the neural network research, but they were revisited, and then they gained quite a lot of popularity. Then now that we are talking about this, part of the talk that I'm going to talk is basically about the compactization. So we are leaving the architecture search out, and then we are going to talk about the compactization, in a specific pruning and sparsification. Before going to the pruning and compactization, I would like to have a revisit, or we have a short recap of a neural network. So basically, we are going to talk about the neurons. So, if I get a biological neuron, which is on the left, I have the cell body, then there are like the dendrites, and then I get the input impulses, and then those are carried through the dendrites to the cell body, and then the impulses that are carried away, that are going through the axons, and then the terminals, axon terminals. And then if we assume that we have a mass of neurons, then these axon terminals are connected to the next neuron, for instance, and so on. So if we take this to the corresponding mathematical model of the neuron, what we have is the one that is on the picture on the right. So we have the synapses that are actually, the weights, for instance, in our weight matrix. And then, the dendrites are basically equal to that, multiplication that happens given an input with that specific weight. And then the cell body just, calculates the output of the result of this. For instance, here is a linear function. And then you have the activation function, and then the output, which is the result. This result could be carried out to the next level of the neurons, and so on. So what I need here is that I'm going to use the terms, synapse and neurons. So we have an idea what the synapse is and what the neuron is here. So let me go to the next slide, where we are going to briefly talk about the sparsification. Let's say I have a simple MLP neuron here, so neural network here. And as you see, for instance, the outputs of one neuron is connected to all the neurons in the next level, and then this moves forward. So then basically what sparsification is that if I do something that actually removes one of those, synapses, or actually by some mechanism, I remove synapses in the neural network, that is what we are going to call it sparsification in this talk. One question could be, how could we remove a synapse? Any ideas? So the answer could be, sort of simple. So we need a criteria for removing the synapse. So people have proposed different ways of doing it. So the easiest one is I could do a minimum weight. For instance, based on the magnitude of the weights that I have, I could decide to put the weight to 0. So I take some measure, and then I just look at my weight matrices, and then put some of those, top K minimum values in terms of the magnitude to 0. So that's when I am, doing some sort of a sparsification. One may decide to do actually the mean activation, basically as a criteria. Or there are like more advanced techniques. So for instance, one is like this Taylor expansion approach, which tries to take into account that what will happen if I remove specific weight, and the optimal brain damage. These two are sort of like connected to each other, different formulation of the Taylor extension. One is from the 90s, and then the other one is from the 2017. So if we would like to apply this into our pipeline for sparsifying a network, we will have something like this. So we take the network, we evaluate the weight of the synapse, or then we take basically based on how much we want to sparsify, we just put aside the k-list important synapses. And then we could fine-tune the method, and then we could repeat this process as long as we want. Of course, there is a key tweak that is, once we are going to fine-tune, we have to make sure we don't backpropagate anything again to those weights that we have put to 0. Otherwise, they will change, and then we lose the removed. We are putting those synapses again back into the calculations. So that's just a simple a step that we have to in mind while implementing this. Then let me talk about what I mean by pruning. So when we are talking about the pruning in this talk, we are basically discussing about the situation that we are removing a complete neuron. So if I have my MLP, then in the hidden layers, I start removing some of those neurons that are not contributing. So how I am going to do this? It is basically either introducing again a criteria that evaluates how to remove one neuron, or during the course of the sparsification step, I may happen to have neurons that they have all of their inputs or outputs put to 0, and they have lost all of their synapses. So I could remove basically the neurons that the synapses or the links are removed in the sparsification step. When we are talking about pruning and sparsification, a good body of the literature uses them interchangeably. But here in this talk, I'm going to use the pruning whenever I am using, I'm going to remove a neuron, so that could cause a structure change. So that, in that case, I'm calling a pruning operation. And if I am doing something that doesn't cause a structure change, like putting just one synapse into 0, that does not, affect the structure, then I will call it sparsification. Yeah. So these sparsification and pruning approaches, they have their own, cons and pros. So in order to get basically the goods of both, with my colleagues, we put, for instance, something together to do hybrid pruning and sparsification. So we decided that instead of doing purely sparsification or purely pruning, we could do up to some percentage pruning, and then up to some percentage we could do sparsification. So we ended up with a very simple algorithm. So we take the network, for instance, for the case of the convolution layers, we take those, and then we look at the convolution layer, and then we have like this filter definition there. What we do is, we just do a reshape, and then we calculate the importance of the output channels, and we decide to remove some of the output channels in terms of the graph diffusion process, which is one way of calculating the importance of these, feature vectors that we have per output channel. So we calculate the importance of the output channels in terms of the feature vectors. We basically do this calculation. We, similar to what I showed you, we drop, for instance, the K% of the least important, channels, output channels in a convolution layer, and then we do a regularized retraining. So what is a regularized retraining? We are adding some regularization term to the loss function to promote the sparsity. So there are different loss functions for that. If we search the literature and the L0, which is a difficult one to implement, L1, that's the easiest one that the people are using, and so on. So we just here we use like a technique that is with some of our colleagues, that's L1 to the L2 kind of a norm loss. And then after retraining, we again do a sparsification. We remove some of the synapses of the network. So this actually surprisingly starts to be doing very well. So we did a kind of a comparison. That's what will happen if we do, purely a sparsification. So if we purely just try to, promote sparsity in a network, then we do pruning by some 10 to 15% of the network to be pruned, and then we sparsify the rest of the network. So we compared these two settings, and then we try to get to a specific compression ratio. And we realized actually on the same compression ratio, on the large neural networks, the degradation, the performance degradation is quite minimal if we do the pruning and sparsification rather than purely unstructured sparsification, as some people have been promoting. And one advantage here is that once you're doing this kind of pruning, that we are actually removing some neuron or some structure, we are saving also the computations without any specific implementation. So for 10% pruning on the VGG, we observed up to 15% speed up in the calculations as well. And that is sort of, interesting to see this. Of course, there are, people who have been, almost at the same time, they were looking into pruning and sparsification. And then they compared this unstructured sparsification against the pruning that leads to removal of some neurons or structures. And you're actually getting to the same conclusion that we have observed. So for instance, this is a result from a research paper, which actually compares two techniques. One is called lobster, that's a pure sparsification. And then the other one, which is called Serene. Actually, Serene complements the lobster, and what it does is it parses the neural network, and then if there is a neuron that has all its incoming inputs or outgoing outputs set to 0 for the reason of the sparsification, then it removes those neurons basically. And as you see, the topology could be simplified, and then there is a speed up in the inference time. Of course, the inference time will vary from device to device in the way that these things are handled on each of those devices, and then the capabilities that they have. And in some cases, actually, we do pure pruning. So this is again from our method that I showed you. if I put this sparsification to 0 and then I only prune and then I try to get to the compression ratio of 0.15, actually, my degradation is quite minimal, given the performance of the original model. But then I could get up to 500 times, saving in the number of the flops that I have, and that also translates to the speed up in the calculation. So I would say probably the take-home message here is, if you want to do some compactization in terms of the pruning and sparsification, we have to consider the cases that could have some, that could bring some benefit in terms of the, for instance, hardware platform that we have, or in terms of the computations that we are doing. So that means we have to take into account the structures of the network, and then we have to enforce some structure that could be exploited either by software implementation, or it could modify the topology of the network in a way that without any intervention from hardware and software implementation, that could save or number of the calculations that we are doing. So at this stage, I am basically wrapping up the talk on the pruning and sparsification. So if there is any question or any comment, we could discuss that. Otherwise, we could jump to the next topic.
There was one comment that this pruning and sparsification, how is this related to dropout, to randomly removing parts of the network?
Mm-hmm. So the dropout is basically an approach which is some sort of regularization, which we are trying to on and off the networks during the outputs of the network during the training, and that basically helps the generalization. In this case, actually, what we are doing is we are looking into permanently putting some of the synapses into 0. So this is something that happens post-training usually. So we already trained the network, and now what we are gonna to do is, we are gonna to remove some of those links that we have. So in a way, it's a different use case than the dropout use case that we have. And then in the dropout, we are not enforcing any structure change, or we don't consider any structure in order to do a speed up at the inference time. So I would put it in that way. Okay, any other questions? Okay, so then maybe we could move to the next topic. So the quantization, I think that's a topic people who are coming from signal processing, they're quite familiar with. And what I mean by quantization, let's say I have like some float values. What I want to do is that I just would like to get those values and map them to lower precision. So for instance, here, what happens is that I have, some real value ranges, and then I have some clipping range here, alpha and beta, which is -1 and 1. And then, anything between these values are mapped to, the range of -127 to 127. That's 8 bits. And, here in this specific case, 0 is mapped to 0. So it's a symmetric mapping from some float value domain into an integer domain in 8 bits. And of course, we could have it in an asymmetric manner. So the ranges the clipping ranges could be different, and then necessarily the zero in the real value could correspond to the zero in the quantized value could be corresponding to some value other than zero in the range in the domain of the float values. So this is basically something that we call it kind of a uniform quantization. So I have some scale value or a step value S, and then I have some clipping values alpha and beta, and then I have an offset Z, which tells me where the zero is. And the interesting thing is that I could actually, if I use this formula to do the quantization, whenever I need, I could do some dequantization and get back my estimate of the original real value also. So basically, since that here we're talking about the uniform quantization, that's actually very popular also in the neural network area. We are going to talk about the neural network quantization. So why do we quantize the neural network? Usually when we train a network, it gives us float 32-bit representation for each weight that I have in the matrix. If I could do all the operations instead of 32-bit floats on some lower precision like 8-bit, that is quite a lot of savings for storing that network, for the computations that I do. If I could do things in the integer domain rather than float domain. So the techniques are usually could be categorized into two big categories, like the post-training and then the training-aware approaches. So post-training, like the weight-only quantization, and in some cases the weight and activation quantization approaches, these are easily could follow the the uniform quantization that we discussed. So we could just get a neural network, apply a uniform quantization on that, and then try to use it. But here we usually hit some problem that's performance degradation. So the more we go to a coarse quantization, less number of bits to represent the network, you start seeing significant degradation in the performance. So that's when the people came with we could do some more smarter way of doing the quantization. That's joining the quantization with some training or some adaptation. So there comes these two approaches that could compare to each other like this. So on the left, I have what we call it the quantization aware training. So in this case, what we do is usually we get our pre-trained model, we quantize it with some quantization operator, and then what we do is that we do some sort of a fine tuning using some data, where the feed-forward pass is in quantized domain, and then in the backward pass follows some in the float domain or the real value domain. And during this training, we try to adjust basically the networks with regard to the quantized values. So we have minimal loss of performance. There's also another way of doing it. So this other way could be done, with less data, because we don't need to do the whole training with this post-training quantization. What we do here is something like calibration. So by calibration, what we do is, we are going to adjust the clipping ranges and then the scale factors of the quantizer for the data that we have and for the condition of the operation that we have. So this sort of a calibration process, is much cheaper in comparison to the training ever quantization, and sometimes it could be actually used or combined with the cases that we are doing some fine tuning in the quantization ever training.
Ahmed, there was one question on the chat. Doesn't QAT require quantization of training data before retraining?
Sorry, could you repeat that?
Doesn't QAT require quantization of training data before retraining?
Of training data before. So no, as far as I know, at least I haven't applied it in such a way. So no, I think we could do it also with the actual float data that we have as the input.
Okay, thank you.
Yeah. Okay. So okay, there is a point. So yeah, also there is a point here to mention. When we are doing quantization, something that we may want to pay attention is the granularity of the quantization. Depending on how we are going to decide about the clipping ranges and the scaling factors and how we're going to adjust it, things could be slightly different. So, for instance, we could start to do the quantization at the granularity of each channel of the convolution layer, or we could decide to do it actually. We have the same clipping range for all the filters of the network in one layer. So this kind of granularity that we are going to choose, that is also something important and a contributing factor when it comes to quantizing a neural network. And then the other thing that probably could contribute, I'm going to talk in the next slide. After we learn about, we could use the vector quantization also for model quantization. So, for instance, for those who are coming from signal processing, the vector quantization is a very familiar term. And then, we have different clustering schemes, k-means, for instance, that we could use to reduce model size. So something that we did with my colleagues was that we applied some kind of a structured vector quantization for the convolutions. So actually, we could assume that there are specific structures which we would like to quantize those, and in this case, for instance, the kernels of the filter. Those could basically be taken as a structure of interest. So one could do this kind of iterative scheme of quantizing. So we take one part of the network, we do some sort of a k-means clustering on the kernels, and then we fine tune the rest, and then we progressively proceed to have some fully quantized set of convolutions. So we tried this and then compare it with some, let's say, other approaches. We called it structure-aware quantization, SAQ, and then actually the method has its cons and pros. It's a very slow method because the comparison of structures and doing this clustering could be expensive if you have quite large number of clusters to consider. And then the other thing is that it usually works when you want to go very high compression. So we we had a use case, and then that was some audit classification, and we compared with 4 other techniques. This NCTM4 is uniform quantization, and BF, UQ, and LSA, they are other techniques of handling the quantized data in a specific platform. It's more a compressing technique rather than quantization. And then when we did this basically FAQ, we realized actually the performance could be quite good when you're on very high compression. So 0.01, and then the performance is 42 versus 20, which is, I would say 2 times the other approaches. But of course, then there will be a question: do we really want to compress it that much, where we are basically degrading significantly the performance? It goes from something 60 to 42 in terms of accuracy. But I see that there is potential for looking into structures and exploiting the structures when it comes to the quantization as well. Yeah. So now that I'm wrapping up the quantization aspect, I am going to talk a little bit about how we could put these things together. So, now that we talk, it seems that we need also some sort of a standard interface for compression of NNs. Let's assume that I want to deploy, models on large number of devices. I want to have a cross-provider interoperability. I get, compress some data update from some specific platform, then I should be able to deliver it and then interpret it also on the other end. So the ISO Institute started, some activity some years ago on the compression of the neural networks. It was recognized as the NNR and recently as NNC, which we were basically actively contributing, and some of the works that I showed you are those that are relevant to this MPEG activity. So it's basically a set of toolbox, and how we are going to utilize these tools in a organized manner, such that we achieve this deployment and across provider interoperability. So we have the parameter reduction, that's basically the sparsification and pruning approaches, and then you have the quantization techniques that we talked, and then eventually the entropy coding that could consist of different, each of these boxes could consist of different tools. These are going to give us basically a compressed bit stream set of bits that we could transfer over the network and and deploy, for instance, or models and devices without using too much bandwidth. Some of the tools in the boxes, like those in the parameter reduction and then the quantization, they could be used for the purpose of speeding up the network for on-device usage. For instance, if we just here look at the bit stream size that is taken with different pipelines, like the quantization plus entropy coding versus sparsification and quantization entropy coding, we see that this becomes quite well compressed in terms of for instance, using the tools that we have rather than having something uncompressed, or using some BZIP2 compression tool rather than the NCTM CABAC coding. And then these two curves have some also interesting thing that is based on the usage or the use cases. One tool in the toolbox may become useful. For instance, if we look at the gray curve that is labeled as UC12B, It's a multimedia compression. And as you may have noticed, actually, that's the use case that the sparsification in the pipeline could help actually the prevent the degradation of the performance, rather than having just the quantization and entropy coding. We have more degradation. Of course, we see the vice versa when it goes to the image classification. For instance, in case of the VGG, I interpret these curves as, it is enough that I quantize an entropy code and, get a better performance if you look at this, blue curve. But of course, if I have, a specific intention of a sparsification, where that could lead into, for instance, a specific implementation that has a speed up performance inference, then, of course, having that in the pipeline still, works, and we are fine, and we are good. So at this point, I think I put the compactization, and, that comes as the pruning and sparsification, and then the quantization together. And then we went into a standard that puts all this together, and then we could, just use this to deploy our models. Then I am gonna move to the collaborative machine learning part. So we could have, probably if there are some questions, we could have, some questions, and then we could continue otherwise with the collaborative machine learning. Okay, then, okay, I move to the collaborative machine learning part, and I hope that I could wrap this in 15 minutes. So, when you're talking about collaborative machine learning, what do we mean? So it is, like the collaboration between participants for getting into a model. So actually, that's like learning a model collaborative. So I think this concept has been quite around for a long time, and it has been revisited, and new tweaks has come into the domain over the years. So, for instance, back in early 2000s, when I was a bachelor student, probably when we were talking about collaboration, it was more some kind of a distributed process. So it was similar to training a network in a distributed fashion. So the workers could be the GPUs on one machine, or they could be multiple machines that are connected through some high bandwidth dedicated connection to a master machine, and then the data is distributed to them. They are working on the data, and then they send back basically the updates that they have in terms of, for instance, the gradients of the model to the master, where these gradients are merged together. But then what happened was, some guys said, okay, this could be quite a bottleneck if you want to do it, let's say, at a scale, and if you want to do it, for instance, on your mobile devices. So they came with this idea of federated learning. So this is basically a very simple, chart that shows how it is working. So different devices, they are requesting to participate in the training of the model, and then depending on this, they are basically the request gets accepted. They get the model that they have, and then they start training that model on their local data. And after a period of time, once that's finished, they send the trained model back to the server. And then, an aggregation operation happens. So what happens here is that they're working on their own local data, and then that is basically local to them. And then instead of sending the gradient updates, which is very frequent, they're going to send this, information after, in terms of some model update, once they have finish training on that data that they have. For instance, after one round of training or one epoch, for instance. So what is the difference between distributed training and federated learning? I would, take the obvious ones here. So I would say, the data remains local. So there isn't any ownership issue. There is no need for circulating the data. So that's quite, saving the bandwidth. So I have my own local data. It's safe with me. I don't share it with you. Then, in terms of the bandwidth, I don't circulate the models. And then also, because I am training the model and sending the model updates, not gradient updates, that's also saving in terms of the number of the communications that I have. So federated learning is one step ahead from the distributed learning in terms of the computation efficiency, I would say. But then this federated learning, this communication, efficient way of training the model, it itself has its challenges of communication efficiency. So let's say, now you're talking about devices. So number of participating devices could increase. And as we go from 1,000 to 1 million devices, this itself could become a communication bottleneck. You're going to be on a, much more bigger scale. We could basically have handful of devices in a federated learning scenario, which may have, issues with the network bandwidth. So it could be that the network that one of these devices is not as reliable as the other one, because you're not on a dedicated transport. You're, just on a regular transport medium. It's my cell phone and then, my Wi-Fi. And, I just go out of this room, I just lose that basically a stable connection that I used to have. So it could be, be on a setup that is not as reliable and as stable as in case of the federated learning or a style of institutes that are collaboratively working on a project. So the other case is that it could be that we have limited edge node computation. So it could be one institute, is more powerful in terms of the computations than the other one. Or if you are deploying and we want to do something, learned on a device that is of low capacity, then we may not be to be, as equal as to a distributed setup. And then another issue is, the statistical heterogeneity. So, the data is local. So it could be that Institute A or device A has a data of 100 images, and then the other one has only one. So this brings us to the non-IID distribution of the data, which could be quite challenging in terms of, the convergence of the learning operation. And the other point is that if we want to communicate, let's say, the models or the weight updates of those models in an uncompressed fashion, we have to calculate the total computations in terms of the communication rounds. That's an upload and download. So I download the model, then I train it, and then I upload something. Then the number of the parameters in that model, and then the bit-width representation that that model has. So for instance, if I took AlexNet, and then let's say I am doing 10 rounds of communication, I have 61 million parameters in this model, and then I want to do it fully on compressed with 32-bit representation per parameter. Actually, that's 4.5 gigabytes of data. Now imagine that if we want to do this in order to train a model, and then we go with, hundreds of rounds of communication, and then we have a much larger model, so we're going to basically having this exploding. So how could we actually improve the communication efficiency still in this federated learning setup? So something to revisit here is we could use the same concepts that we talked beforehand. So we could try to, at least when I am sending the models, I could do the same sort of a compression as I was doing in the MPEG standard. That's one way of doing it. And actually, this could be done easily from the server to client. In the normal federated learning, the assumption is that we are always sending the model from the server to clients, and the weight updates are going to be communicated from the client to server. That's the simple scenario. And now that we have something for part of the solution, what about the other part? In order to talk about the communication efficient federated learning, I categorize the algorithms into two sets. I would say there could be algorithms that are agnostic to federated learning. So they are not taking anything into account with regard to the environment, the communication channel, the model. If there is a specific algorithm on the aggregation side, they are totally blind to what is happening. So they just take something and then they try to compress it. They just know it's a weight update and it's a weight of neural network. Then I could talk about the specialized methods. These are those that are making specific assumptions. So I would say, we could consider, a specific averaging algorithm, proposedness, model properties, and etc. So I'm going to talk about this. And Alex, I have some 10 slides left. And would it be fine if we go over time?
Yeah, so how much longer would you need? We have 3 minutes left.
Yeah, so if I want to wrap up this, I think that will take probably some more time, maybe some 10 minutes or something like that.
Yes, 10 minutes is fine.
Yeah, okay. So I try to wrap it up in 10 minutes. Okay, so let me give an example of a specialized algorithm that we call it specialized. So, we could assume, there is an algorithm that is called federated trained ternary quantization. So that there is a very famous way of optimizing the models for efficiency, and that's a ternary representation of a model. It's a very efficient way of inferencing information, and that actually could be implemented with XNOR operators. So here, for instance, there is an algorithm that assumes that we are going to do ternary quantization for the communication under the condition that at inference time, also the global model would be in ternary representation. So with this kind of assumption, these guys are formulating basically the problem of compressing the weight updates and then the model. And since the model is also, in ternary quantized form, it's very compact and efficient for compressing both the uplink and the downlink. There is one thing that here to mention, actually, when we talk about the compression algorithms, this is an unbiased compression scheme. And that means actually, if you have a compression algorithm or operator, we could actually recover the original input to the compression algorithm. So another example of these, specialized algorithms are those that are taking into account the communication channel, as I told you. For instance, these guys are assuming that we are on a multi-access channel, and then they do some sort of a channel-aware quantization of the model, and there are many people in the telecommunication industry who are adding this kind of a communication channel constraints to their model quantization approaches. And I am cutting things short, so I quickly go to the techniques that are agnostic to the federated learning. As I said, we try to compress weights independent of any application. No assumption about underlying algorithm. So it could be that we just send the weight update and it is used as the weight update. And no assumption about communication channel, so we don't think about that area. And we are assuming that we get some model and then we reconstruct the same model at the output. So we don't have any assumption that this is going to be used quantized or that's the same thing. So actually, this is what we are doing in the second version of the NNC standard. And one of the, for instance, algorithms that we worked on was one of the algorithms that could fit into this kind of a category of the algorithms is a sparse binary. So that's actually from a group in Germany, and that is you could just do something that is called weight update or gradient dropping. So we just we just keep up k%, and then we move the gradients towards one of the directions that is stronger. So either towards the positive steps or towards the negative step of the gradient. And actually, this is shown to be working very well. So the SDC here in this table, it is on par with federated averaging in terms of the performance. And then if we look at the baseline, that's like training the network locally, and then if we do it with gradient dropping, which is just a sparsification, compared to the federated averaging, it's quite a huge boost in the speed of the in the compression of the communications. So they could get up to 3,000 times compression. And so we basically at Nokia we try to be agnostic, and then we apply we proposed kind of an approach that's a hierarchical quantization. So we apply two levels of quantization. So if the model that we are getting is already in float domain, we first do a uniform quantization. And then what we do is some sort of a stochastic binary ternary quantization. So what we do algorithmically is described here. Just like, I just, what I do is that I randomly choose whether I'm going to do a binary quantization or a ternary on a model that is already uniform quantized. And then I communicate basically those information that are relevant to the binary or ternary one. So it's either so that scales and the assigned bits relevant to the and the signs relevant to the bit masks. So our selection criteria is basically a Bernoulli function. So we try to initially go with as much as possible with the ternary quantization, and later as we are converging over the time, we switch more to the binary, where we could say it's more pedestrian without the danger of losing the convergence. So if I look into this, so first of all, if we just have a model and then we apply binary quantization on a federated learning use case, that's the red curve. As you see, performance-wise, it is not as as good as the ternary quantization. And then in terms of the bit stream, actually there isn't much of a difference between this, ternary and binary. Of course, binary is smaller, given the same amount of rounds of the communication that we have. It's smaller, but the degradation is much more. And then you have this uniform curve. So that's if I just get my model to uniform quantization. Interestingly, it is more compact and having a higher performance when I compare it to the binary and the ternary approaches. But now let's say I put this stochastic binary quantization on top of this uniform quantization. That's actually quite interestingly, we get to the same performance, and then we are saving actually quite a lot on the bit stream in, let's say, 10 rounds of communication. So here we have the results for the unidirectional. That's from the clients to server compression, and then the bidirectional case. That's we compress both sides, the communication from the model to the clients, and from the server to the clients, and then from the clients to the server. Of course, we also tried this on another case, that is basically when we have a multimedia application. So I am training a model, and I have the counterpart model already on some device, and then what I want to do is that I just want to send some model updates to that specific device to improve its performance. We tested this uniform SPT here also. Actually, it results in much more compact bit stream, but since this is like kind of a training approach that you're doing, the convergence is like lower in comparison to the uniform, but still, it seems quite a good tool for delivering an update to a model that is already trained. So given, I think this, I probably could end the talk. I think I've covered everything that I wanted. So probably if there is some questions, I would be happy to take them.
Thanks a lot, Hamed, for your excellent talk. Really very interesting overview of the current state of the art in industry in federated learning. So does anybody have questions, please? No questions so far. So I would be interested how far away are all these experiments and these ideas that you talked about from being implemented in standards or from standardization?
So the things that I discussed is basically the toolbox that I showed you.
Yeah.
So actually, it contains the tools that are consisting of basically the sparsification and pruning approaches that I talked about. We have even some more tools there, like the batch non-folding, local scaling, decomposition-based techniques, and we have a set of quantization approaches. So we support the uniform quantization, and then we have different implementations. We support the codebook-based approaches, and then we are In the NNR v2, we are having basically this variant of the SPT that I showed you. There, it's implemented in the standard. And then we have different entropy coding tools, and then the best of them has been this deep CABEC. It's a CABEC variant that has been very useful in the standard. So many of these are actually in the toolbox, and they are implemented, and then they are tested. We are expecting that by the end of the year, this NNC standard probably would be final version 2 also, and it would be available to the industry for those who are interested to use it and adopt it in their industrial applications. So I would say many of these are sort of supported or implemented in some way in the toolbox.
Okay, thanks a lot. There's one question. How about support for ternary computation in today's embedded architectures?
Mm-hmm. So you know, we are trying to be agnostic to the hardware platform. So in this stage, the standard has put the you know, the ternary implementation aside. So we don't have the standard way of, you know, implementing the ternary in this standard covered. We are more on the side of how things should be, you know, packed and delivered. So if someone has a ternary model, that would work totally fine. So, you know, this standard would work for transporting that. Then it's up to the user to take into account the hardware specification of its implementation. But
Okay.
we have the tools for signaling that. So you're getting the model that's ternarized, you know how to handle it. So we don't go into that hardware part. It's out of our scope.
Okay, thanks a lot. I would say we wrap it up at this point. I assume you are happy to take further questions by email. You can find the contact of Hamid on the school side. And yeah, it would be great if you could share with me the slides so I can put it on the school side afterwards.
Yeah, sure, definitely. I will send them to you by this evening. And thank you for having me in this summer school. Thank you so much.
Thanks a lot, Hamid. Have a nice day.
You too. Thank you. Bye-bye.